viewers to another episode on ASUG 12 exams. So in this episode we are now looking at section C of the 2021 Internal Science paper 1. So in this section we're expected to answer only 2 questions out of 3 and each question carries 10 marks. Let us look at question C1. Question M, describe an experiment on how you can determine the lower fixed point of a thermometer. So basically in this case it's just determination of the lower fixed end point of the thermometer. So what we do is basically let us move to the new page. So to determine the lower fixed point of the thermometer, what we do is the first step, what we need to do is basically we need to immerse the bulb. So the bulb of the thermometer, now this thermometer is uncalibrated. So the bulb of the thermometer is immersed in pure ice water. So what we do is basically we have pure ice water. So there is ice and water, we immerse it in there. So once we immerse it in there, basically what is going to happen is this is the uncalibrated thermometer, just a laugh. So once we immerse it, basically the liquid column, this liquid column could be of mercury or alcohol. If it was from here, it's going to fall down to a constant length. So this could be the constant length. Now because this is pure water, the constant length, this should give us 0 degrees Celsius. That would be the constant length. Then we mark this length. Okay, so mark the level of liquid column where it falls, column when it falls to a constant length. Okay, we mark this one. So once we mark this one, this is basically the lower fixed point of the thermometer. So basically this is how you carry out this experiment. So the other question that you might be asked is also to describe the experiment briefly on how you can mark the upper now fixed points of the uncalibrated liquid thermometer. So again, similarly, what you do in this case is basically now we are not putting or you're not immersing this uncalibrated thermometer into pure ice water. Now you are immersing it in pure steam water. So pure steam water. So in this case we're using the steam of the pure water. So once you put this one, it will start from somewhere. Whether it was here, it's going to rise until it reaches a constant maximum. So this constant maximum for pure water, you know that the steam for pure water is 100 degrees Celsius. So once it reaches a constant, this constant, you mark it. Once you mark that one, this one becomes basically the upper fixed point. So this one becomes the upper fixed point of the thermometer. So basically this is how you answer this question, whether it comes the way this question comes or the other kind of a question where you're asked to demonstrate how you determine the upper fixed point. Let us look at B. Give 2 differences between a laboratory thermometer and a clinical thermometer. So it's a lab and a clinical thermometer. So let us go to the new page. So B, we are going to have a laboratory, then clinical. these are thermometers, so I want to compare the two. So basically, number one is the laboratory thermometer is used for laboratory experiments. Then a clinical thermometer is used for clinical purposes in this case, because these are normally the actual activities, they are not experiments. Number two, basically the temperature ranges on this one. The temperature ranges from -10 degrees Celsius to about 110 degrees Celsius. On the clinical thermometer, the temperature, because this is meant for the body temperature, the temperature ranges from 35 degrees to about 42 degrees Celsius. And next on the bonus one, number 3, the laboratory thermometer does not have a kink, so does not have a kink. Then number 3 here, the clinical thermometer has a kink. So the kink is basically helps. So the kink helps to prevent the backflow of mercury if you're using mercury or alcohol. So basically these are the differences between the two. Let us look at question C. Mention one way in which you can improve the Roman numeral 1 sensitivity of the thermometer. So there are 3 ways, basically the key ones, but in this case we are requested to mention one. So basically we can improve the sensitivity of the thermometer basically by using thinner wool. So the first one in this case would be using thinner wool, because if the wool is thinner, then heat will travel quickly inside the liquid used. Then number 2, just as an extra one, you can use a smaller bore. This would also make the liquid there, if it's mercury, to respond quickly. Then if you are using mercury, number 3, we can also use basically a smaller mercury bulb. So number 3, we can use a smaller mercury bulb. This would improve the sensitivity. We look at question number Roman numeral 2 of C, accuracy of the thermometer. So we can improve the accuracy of the thermometer in this case by basically by using closer markings. So if the markings are closer, this will allow us to capture every small movement. If these markings are very close, there will be no area where we need to guess if it's the leading force or the in between the markings. So basically this is how you can improve it. We go to D. Name a device that can be used to measure very high temperatures and those that vary considerably. We move to D. Name a device that can be used to measure very high temperatures and those that vary considerably. So basically this one is a thermocouple. So it's a one that is used to measure very high temperatures and those that vary considerably. So a thermocouple is basically a temperature measuring device which consists of 2 dissimilar conductors. that contact each other at one or more spots. So basically what happens, it produces a voltage when the temperature of one of the spots differ from the reference temperature at the other parts of the circuit. That's how it works. Question D, Roman numeral 2. Mention two devices that uses a device you've mentioned in D1 above, which is the thermocouple. So basically, there are a number of devices that uses a thermocouple. One of them is, let me just go to the new page so that you see the spellings correctly. So number one is basically the thermopile radiation sensor. So this one does use the thermocouple thermometer. Number two, basically this is the thermoelectric cooling. Again, this one uses the thermocouple thermometer. These are the two. The bonus are furnaces. So furnaces in steel industry, they also use the thermocouple thermometer. So basically these are some of the key applications that are used with a thermocouple thermometer. So basically this is how you answer these questions to get the optimal marks. Let us look at question C2. The following data was obtained from an experiment to determine the focal length of a biconvex lens. Then we have this table, U and V, they are measured in centimeters. A, copy and complete the table to get all the values of M, which is magnification. So M is given to us, which is just V divided by U. So this is just a matter of finding the values. So what we do is we start with here. Basically, a 44 divided by a 30, we are going to end up with 1.467. But since this is given to one decimal place, we're going to write it to one decimal place, which will be 1.5. Then next, to be 37 divided by 35, we are going to end up with 1.057 to one decimal place. This is going to be 1.1. Then we have 32 divided by 40, which is going to give us 0.800 to one decimal place. It will just be 0.8. Then next, 31 divided by 45, it will be 0.689, which is to one decimal place, it will be 0.7. Then next, it will be 28 divided by 50, which will be 0.56. Then to one decimal place, it will just be 0.6. So basically, this is what we are getting. Then once we do that, we get this 2 marks. Question B, plot a graph of M against V. So it's magnification against V, which is basically the distance of the image from the optical center. So basically what we need to do is basically we need to understand the distance here. We are moving from 44 as the maximum number, then 28 as the smallest number. So basically it's 28 to 44. So basically what we can do is, because this is not starting from 0, we can start from maybe 25, increase in the interval of 5. So we have 25, 30, 35, 40, then 45, like the same scale. Similarly here, we need also to know the maximum is 1.5, then the minimum is 0.6. So we are again not starting from 0, but this one you can start from 0, maybe you can increase it in the interval of 0.25, then 0.5, then 0.75, then 1, then 0.125, then all the way up to 1.5 or 1.75. Then once we do that, this, remember, M is the y-axis, then V is the x-axis. So once we understand this, we can move to the graph and label these correctly. So we have a graph that I've labeled because I had to post the video so that you don't have to waste so much time. So what we do is basically we have labeled a V correctly, then also M correctly, then also the interval as I had explained. Remember, this is not starting from 0, but this one is starting from 0. So you put this car to ensure that there is a jump. Then once we do that, basically we can start plotting. So we have basically 1.5, which is this one, comma 44. So 1.5 is along this line, then 44. Remember, these are in the interval 5. And there are 10 subunits, so it will be 5 divided by 10, which is 0.5. So each subunit is 0.5. So what we have is basically 44 is basically these minus 2 subunits, so it will be somewhere basically here, somewhere there. Then next we have 1.1 comma basically 37. So remember, these are increasing in the interval of basically 0.25. So 0.25 divided by 10, we have 0.025. So basically two of them, they will give us basically a 0.5, a 0.05 unit. So basically, if you're looking for 1.1, we need to move these 4 of them. So 1.1, 4 of them, so it will be just before 5, comma 37. So 37 is 4 of them here somewhere. So we move 4 subunits. So it will be somewhere here. Then next we have 0.8, which is just 1 subunit or 2 subunits above 0.75, then comma 32. So basically 32 is basically 4 subunits somewhere here, then along, so 4 subunits, so is somewhere here. Then next is 0.7, then 31. So 31 is just 1 subunit. 31, 1 subunit, comma basically 0.7, which is just basically somewhere just below here. So it should just be somewhere here, somewhere there. Then we have 0.6, comma 28. So 28 is just basically 4 subunits below 30. Then so which will be somewhere below 30, comma okay, then comma 0.6, which will be basically 4 subunits above 0.5. So we have 1, 2, 3, 4, then 4 subunits, so it will be somewhere here, so somewhere there. Once you do that, then you join these with a best fit line like this one. So this line is basically the best fit. We should pass through these points. So basically this is how you answer. So you join it nicely using a sharp pencil. Then once you do that, you have basically the 4 marks. Then next, determine G, the slope of the graph. So the slope of the graph, G, is given by basically the change in M. So it will be M2 minus M1 over basically V2 minus V1. That will be basically how we find the change. So basically once we find the change, so let us pick 2 extreme points because it will just be an average. So just going to pick 2 extreme points on the table. So G in this case will be basically we are going to say a 1.5 minus 0.6 over basically 44, because this is 28. Okay, once we do that, basically we know that this is the same as 44 minus 28. We have basically at the bottom 16. Then we have 1.5 minus 0.6. We are going to end up with 0.4. Then dividing this, we are going to end up with 0.057. This is basically the slope. Let us look at D. Use the slope G of your graph to determine F, focal length of the lens, using G is equal to V over F minus 1. Okay, so let us solve for F in the first place. When you solve for F, then basically we can know what to do. So we are told that G is equal to V over F minus 1. Then we know that basically 1 moves the other side, becomes a positive, so G plus 1 is equal to V over F. Then we cross multiply, we have F multiplied by G plus 1 equals V by doing the cross multiplication. Then F is equal to basically V over G plus 1. So this is the formula. Then we know what G is. So G is basically equal to, we found it to be 0.057 to 3 decimal places, 57. Then we need to know what is the value of V we are going to use. Now, because we are given a number of values of V, so basically the best way to do this is basically to find the average of V. Because ideally what you're supposed to do is we're going to find the focal length for each using this formula, then find the average of the values we're going to find here. Find the average, and that average will be the focal length. That's the standard way of doing this when you're doing an experiment. But the quicker way is basically to find the average of these focal length, then just use 1 to still get the same answer. So what we do basically is to add these values. We add all these. Then we divide by 1, 2, 3, 4, 5 to find the average. Then this average is the one that we're going to use as V here. So basically, we start summing the sum of V. It will be basically 44 plus 37 plus 32 plus 31 plus 28. This will give us basically 172. Then finding the average V, it will be basically equal to 172 divided by 5, which will be basically equal to 34.4. So this 34.4 is the one that we use. Therefore, frequency equals basically 34.4 divided by G, which is 0.057 plus 1. This will give us basically 32.5. So 32.5 is basically the focal length. So just ensure that the units are captured correct, which should be 32.5 centimeter. So remember, it's very important that you indicate the unit as you find your answers. Okay, let us proceed. We look at question E. Mention one use of this type of lens. So now, which lens are we talking about? So we are talking about basically the biconvex lens. So the biconvex lens is also known as a double convex lens. So the double convex lens has a number of uses. So in most cases, basically these uses are focused on two things. It's either you are magnifying or condensing the lens. So basically, among the key applications that uses the double or biconvex lens are basically the one telescopes, number 2 microscopes, number 3 binoculars. So you can choose n of this, just in case you came across the question that asks you to list more than one. So we have cameras, then we have 5 projectors. So all these, as you see in this case, they use these lenses. The projectors is for magnifying. Telescope, you are seeing, and microscope, you want to see things that are far. So these they use to magnify these objects to make sure that they look big. So basically these are the key uses that you need to know. So this is how you answer this question. Let us look at question C3. State Hooke's laws. That's question A. So basically just explain what Hooke's law is. So Hooke's law states that the force or load applied to a spring is direct proportion to its extension, provided it does not pass the elastic limit. That's what Hooke's law states. So basically what is key in this case is a force applied is direct proportion to the extension, so extension of the spring, provided we don't go beyond its elastic limit. Because if you go beyond the elastic limit, the spring is going to be permanently stretched. Then this will not hold. So that's what we need to state. 1. The force applied to the spring is direct proportion to its extension, okay, provided we don't go beyond the elastic limit. That's what Hooke's law states. We go to question B. The following table shows the readings of a pointer of a scale for different masses attached to it at different intervals. Roman numeral 1, copy and complete the table to determine the force acting on each mass on the spring. So basically we know that a force is a function of mass and the gravity or acceleration. So we know that gravity is 10 Newton per kg. So to find force for the first mass of 0, it will be just basically 0 times 10, which will give us basically 0. So this one will be 0. Then for the next one to be 0.2 kg multiplied by 10, which will be 2 newtons. Then the next one to be the same, so it will be 0.4 times 10, it will be 4, then 6, then 8, which is 0.8 times 10. Then that's the force case. Then Roman numeral 2, plot a graph of force against extension. So a force we know is moving from basically 0 to 8. So you see the intervals of 2 newtons. Then extension, so we've been given the pointer leading in millimeter. We know that before we put any mass is starting from 120. So 120 is basically the 0 or the starting point. So to find basically extension, what you can do is basically from 120 to 26, the extension is basically 126 minus 120, so this is 6 millimeter. Then similarly 132 minus 120, so we have next it will be 12, so this is 12. Then 138 minus 120, so this is going to be 18. Then in this case 144 minus 120 is going to be basically 24. So these are the extension starting from here 120, which is basically more like a 0. So this would be 0 for you to understand what is going on. So in this way it will be much more easier, because this is the leading, not the extension. So the extension is the difference with the reading before putting any mass. So once we have these numbers, we can proceed and plot this on the chart. So when you plot this on the chart, it will make more sense. like this. So remember, force will be on the y-axis, which is the first one, then extension will be in the x-axis or on the x-axis. So now what we notice here in this case, the interval is from basically 0 all the way to 24. So we can increase in the equal intervals of basically according to the graph, so that they are in equal intervals, so that the graph is well scaled. Then so let us move to basically the graph, then plot these coordinates. What we have here, we have the graph labeled nicely. So what we know is the extension on the x-axis in millimeter, then a force in newton. So make sure to label it nicely. Once you do that, it will be much more easier work for you to do. So the first one is 0,0. Basically when it's at 120, there is no extension because we are just starting. Then when we apply a force of 2 newtons, the extension goes to 6. So it will be at 6,2. So extension is basically a 6. Remember, the extension is increasing in the interval of 3, 3. So it's in the equal intervals from 0 to 3, 3 to 6, 6 to 9, all the way up to 24. So we have 2,6, which is at this point. Then next it will be basically when the force is 4 newtons, the extension is up to 12, so it will be somewhere here. Then next it will be basically when the force is 6 newton, the extension is 18, so it's 6,18 somewhere here. Then next it will be 8. When it's 8, it will be basically 24, so it will be somewhere here. Then once we do that, you can join these points using a straight line like this. So this is basically the plot that we are required to do to get basically the 4 marks. We move to Roman numeral 2. Determine the extension for a force of 5 newtons. So 5 newtons, remember these are increasing in the interval of 2. So this is 1, then this is 3, then this is 5. So 5, you join 5 this line all the way up to this point where it meets this one, then it comes down. What you notice, this is exactly 15. So the extension itself, extension is basically 15 millimeter. Then the leading on the pointer leading, it will be basically 120 plus the extension, which is 15, which is going to be basically 135 millimeter. That will be the leading on the pointer, but the extension itself is 15 millimeter. We go to question C. Differentiate between plasticity and elasticity. So plasticity and the elasticity. So the idea is just for us basically to distinguish the two. So for us to distinguish the two, what we do, let us move to the new page. So when you're talking about plasticity, so plasticity we are talking about basically the property. So this is just the property of solid materials, that it does not gain or regain its original shape and size after the removal of applied force. So basically, once you apply force to certain solid materials, they do not regain their original shape. Their shapes are permanently changed. In that case, we're talking about plasticity. Then on the other hand, when you're talking about elasticity, this is basically the property of solid material again, that it gains its original shape and size after the removal of applied force. That is basically elasticity. So the difference is plasticity, once you apply force, the shape and the size is changed. Even if you remove the applied force, it will not go back to the original shape. That is the material, a solid material. Then elasticity, you can apply force and change the size and the shape. Once you remove the applied force, it returns back to its original shape and size. If that happens, that we are talking about elasticity. So basically, this is the difference between the two.